Welcome back, calculus students. Can you believe we only have 6 weeks of school left? And really, that makes only 18 e-learning days. Guys, we can do this. Uh, we really just got a little short unit to wrap up uh, our learning before we get ready for reviewing for AP exams and everything. You guys will want to stay tuned this week. We're going to have some really important information for everyone. You guys who are taking the AP exam will have some information for you, like dates and times. Uh, those have all been set up now, so we know when the exam will be and what time you're going to take it. You dual credit students, we have some important information coming this week for you too, so please stay tuned for that. Anyway, the last unit of the course is called differential equations. You guys have already been introduced to this topic. The very first day we introduced the term antiderivatives. We're just going to go a little bit deeper into that topic now. And by the way, you could, if you plan on taking more math in college, etc., you can take a whole semester or two just about differential equations if you really wanted to. You guys going into physics might find yourself having to do that. Anyway, let's get right to it here. Now, really the basic way to introduce the topic is to say, well, what a differential equation is an equation or a statement where there will be in other words, there's going to be an equal sign, and somewhere on one or both sides of the equal sign is going to be a mention of some function's derivative, and maybe even a function's second derivative. But let's take a look at the two examples we have at the bottom of this screen here. Now, the one on the left, this one looks like something we know how to work with. Now, a differential equation is an equation where the derivative is mentioned, and the goal in working with differential equations is to know what is the function whose derivative is mentioned in the equation. So there's a lot of similarity between talking about differential equations and working with antiderivatives. And so, in fact, so when we say we're solving a differential equation, you're actually wanting to find the function whose derivative is mentioned. Now, the two examples we have at the bottom demonstrate really two different kinds. One, the derivative symbol y prime is equal to an expression only involving one variable, only involving x. So if you just kind of say this to yourself, the derivative of y, or the derivative of some function, is 2x. Well, that shouldn't be a big mystery to you. We know what 2x is the derivative of x squared. So I'll just change the color here. And we probably should already know x squared, or x squared plus any constant, is the function whose derivative is 2x. And so we would call this the general solution to our differential equation. Now, we also know how to find what's called a particular solution. If I had told you, in addition to the derivative being 2x, that the function that we're looking for has to pass through a particular point, like let's say the point 1, 2, then we know how to find the particular solution by figuring out what the integration constant is. And so let's just say we had that. If I knew the point was 1, 2, we'd plug in the 1 for x and get 1 squared plus c equals 2, and we'd figure out pretty quick that that constant is 1, right? So if I use the point 1, 2, we would end up with the solution y equals x squared plus 1, and this is called a particular solution. Okay, so this is kind of what we have already done with differential equations. Some situation where you're given a derivative, it's one you recognize, or with all the integration lessons in the last little while, how to find the antiderivative of what's been given. Okay. Now on the other side, though, we have a little different situation. The derivative of our mystery function is expressed in terms of two variables, x and y. Now, this is a little bit different level of difficulty here because it's not obvious by looking at it, how we're going to approach that one. So what we're going to look at today is some situations or other ways to maybe study this derivative without maybe needing to know how to solve the differential equation exactly. And one of those ways is to draw a graphical model known as a slope field. So today's lesson really is about drawing slope, what we call a slope field, to study a differential equation that may not be easy to study using traditional algebra methods. Okay, let's show you what a slope field looks like first. And I made up another differential equation here, and this one also involves two variables. And the equation says the derivative of y, dy dx, now notice we're using that notation now also, is equal to e to the x minus y. Now I really don't think we have any easy way to know what the function y might be. Okay, but what the equation still tells us is that at any point on the graph of our mystery function, the slope can be calculated with this formula. Okay, so let me just guide your eyes over to this graph now. We've never seen anything quite like this. What essentially we do to get a visual picture of what the mystery function may look like is to, at individual points, once we know the ordered pair completely, the x and the y, the differential equation gives us information about the slope, right? So let's say I was at the point 0, 1. Now I have to tell you, this graph actually counts by halves. So the point 0, 1 is right here. Okay, I'm going to point 0, 1 is right there. Okay, because every tick mark is actually a half a unit. So let's say we're at the point 0, 1. And now I go over to my derivative and plug in 0 for x and 1 for y. So according to the formula, the derivative would equal e to the 0, remember that's 1, minus y, which is minus 1, and the slope is 0. So now I want you to remember that underneath this red dot was a little line segment that was completely horizontal, representing a slope of 0, right? So that's how we represent the slope of the graph at that particular point, is to draw a little sliver of a line segment whose slope is what we get by calculating it with the derivative or differential equation. Let's pick another point a little bit further away and see how it matches also. So let's go a little bit to the right, like if I go over 4 tick marks, that would be to the 2, and let's just say 2, 0, because let's say it was this point right there. This is the point 2, 0. If I go over to my derivative now and make this e to the 2 minus 0, well, e, without using my calculator, I know e to the second power is somewhere between 2 squared and 3 squared, so it's between 4 and 9. Either way, that's a pretty steep positive slope, and you notice that the line segment we drew there is a pretty steep positive slope there, right? And so the other thing I'd be able to tell pretty quickly is this e to the x is going to have quite a bit to do with the slope as I move to the right. So like e to the 3 and e to the 4 become very large. So all of these points that have large x values have very, very steep positive slopes. Okay? Compared to over on the left side, when you start to do e to the minus 1 and e to the minus 2 and e to the minus 3, those become very, very small and almost 0. And therefore, the y value has a lot more to do with the slope. So you see a lot of negative slopes over here where the y value is positive in the left quadrant because it's almost like doing 0 minus y. And in the lower left quadrant again, because the x is negative e to the negative 2 and e to the negative 3 is almost 0, it's almost like doing 0 minus y, and so you get, with these points in here, a positive slope here. Okay. That being said, we could now make a guess as to what the solution curve, or what the mystery function does if it had to go through one of these 2 points. So maybe I'll just erase the second one for a minute. And let's go back to the point 0, 1 and say, well, I have no clue what the function is that has this derivative, right? The derivative is involving both variables x and y, but I have a good visual now of what the graph may do if it had to go through this point, right? So it looks like if I move to the left from this point, generally the curve wants to go up. Okay, and it's going to tend to go steeper and steeper the higher we go. As we move to the left, these line segments tend to want to deflect us up also. So it looks like we're going to want to go, generally like this. Now, this is not an exact science to draw this. The idea is we definitely don't want to, go against the grain, so to speak. If we find that we're crossing rigidly through a line segment, we're probably not drawing it right. Okay, now notice, if we had started at a different point, we might got a drastically different shape. Because if I had started down here and I said, okay, let's draw it again, but maybe have to go through 0 minus 1, let's pick a different color here, like green. Okay, so if I had to start here at 0, negative 1, this time moving to the left, it's going to tend to deflect us this way. But then moving to the right, we would still tend to go up. Okay, so again, using the little line segments in our slope field to guide how we draw the possible solution curve. Okay, well, your main objective today is to try and draw one of these slope fields. So let's go and take one that's actually got 2 variables in it. Okay, so I've got one that has both y and x, and the derivative is given by negative y over x. And so what we're instructing you to do is at the indicated points. In fact, we're going to make this a little bit less here by eliminating a few of the points. In fact, I'm going to go ahead and do that now. Okay, so we're not going to draw anything here or here. In fact, you know what? Let's just also get rid of this. Okay, so we're only going to draw them between -2 and +2, both directions. That reduces the work a lot. And basically at each point, we're going to compute the slope of the function by taking y divided by x. So let's actually just start. And what I tend to do is kind of go in rows or columns and do them across or down. So if I were to go across the entire row where the y coordinate is 2, okay, so in other words, the slope in my curve is always going to be negative of 2 divided by something, right? Let's start actually in the first quadrant. If I'm at this point 2, 2, the slope according to the derivative is going to be the negative of 2 divided by 2. 2 over 2 is 1, and the slope would then be -1. Now, if you're on paper, you would maybe take a straight edge and aim your straight edge exactly to a slope of -1. Well, I can kind of do that with my pen and say that's about, like there, aiming for that next dot up there. Okay, that's going to be a slope of about -1. If I move over to the next point, the y value still is 2, but the x coordinate is 1. So it's now going to be -2 divided by 1. And that slope is steeper, but still negative. If we get to the point 0, 2, now the y is 2, but the x is 0, that is an undefined slope. Now, some people tend to leave that just completely blank. What I like to do sometimes is actually just put that as a vertical, because really that's infinite rise, or any rise but no run, right? So really that's a vertical line. So I think that's what I'll do there. If I move across a little more, This is the point -1, 2. So the y value is still 2, but the x is now -1. So 2 over -1 is -2, but then this negative brings it to a +2. It's going to go like this. Okay? And then finally, I've got the point -2, 2. And so my slope would be -2 over -2. Sorry, 2 over -2, which is -1, and then this negative sign makes it a +1, so it's going to be a little bit less steep again. Okay, now what I'm going to do is I'm going to fill in the rest of the slope field. I'm going to pause the video, fill the rest of the slope field in, then come back and talk to you about how we're going to use it to accomplish the next task. Okay, so I filled in the rest of the slopes for the remaining points. So a couple of things to point out. One point I did not draw anything for. It was the point 0, 0, because really I'd be plugging in 0 over 0, and it really is not clear what that is. Remember, that's really indeterminate, so we did not put anything there. However, every other point where the y value is 0, the slope would be 0. So these are all horizontal slopes along the x-axis. And you know what? I just noticed that we didn't put the other two verticals in there at these 2 points here. Okay, now, so what I'm going to ask us to do now is to sketch in a possible solution curve that contains the point 1, 1. So let's just highlight the point with a red pen there. Now what we want to do is use the directions in the slope field to guide how you might predict the curve would go if it were to go to the left or right of that point. Now, the first thing I notice is that point has a -1 slope on it. So if I move immediately to the left, it's going to have to go up. And if I move immediately to the right, it's going to have to go down. Now, we noticed when we were drawing it that as we moved, from left to right here, the slopes tend to get shallower. Okay, so what's probably going to, and then they're practically 0 here at the x-axis. So it would be pretty common to suggest that we're going to continue to go down, but get flatter and flatter. In fact, this might be a horizontal asymptote out here. And as we go to the left further, if we go left and up, the slopes tended to get steeper. In fact, they became vertical here at the y-axis. So it's pretty possible that this is a vertical asymptote right there. So this is my guess as to what the solution curve, or what the mystery function is, who's got this derivative. It looks probably like this curve right there. Maybe a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. So guys, what you're going to do today in the exercises is you're going to draw 4 slope fields just like we did here, just at the indicated points. Be careful with your positives and negatives and things. Now, what I usually tell the students is we're not going to, I'm not going to take my ruler and measure every single one, but I can certainly tell by looking, I know what the pattern is supposed to look like. For example, you can tell that everything in quadrant 1 has a negative slope, for example. Everything in quadrant 2 has got a positive slope. And as you tend to move to the right, they get less steep. And if you tend to move to the left, they also get less steep this way. Okay, so those are the things I'm looking for. And then you're given an ordered pair for each one, and you're going to mark that dot and then use your slope field to make a guess as to what the curve is supposed to be doing. Okay, just like I did there. The other exercises are a little different. You're going to be given 4 differential equations and 4 slope fields. You're going to try and match which slope field goes with which derivative. Okay, so good luck with that. Let me know if you're any problems or concerns. And again, stay tuned for more information this week about AP exams and other things, guys. We'll look forward to hearing from you soon. Thanks.